Hi everybody, in this lesson we're going to be continuing with our journey in analyzing entire functions. That is, analyzing the control flow graph among the basic blocks in a function, doing global analyses and optimizations. The first bit of this video is going to be a bunch of definitions, so you'll need you to bear with me for a little bit. Also, I should note that I just donated blood, so this might get a little bit weird. Thanks for bearing with me. I'm going to use this example program that's on the screen for a bunch of these examples, for these definitions rather. This just has a loop with an if inside of it. I'm drawing also the control flow graph of the Brillified version. You can see the TypeScript, which is actually legible, and then the Brill control flow graph with the instructions inside the blocks. Nothing is terribly surprising here, but like this structure where we have both ifs and loops and the way they interact will be important for the definitions that are coming up. The first definition I'm going to throw at you is one that you are already familiar with. We've introduced it a couple of times in the last few videos, but it's predecessors and successors. So relative to a given block, the basic blocks that have in edges to that block are called predecessors, and likewise the ones that follow it in the control flow graph are called successors. I think that is fairly straightforward. We will also say path quite a bit. A path through the control flow graph is just like a path in any other graph. That is, like, it's just a chain of edges, of like sort of connected up edges going through the graph. And really, this is the same definition as from graph theory, but paths through CFGs are going to come up quite a bit. So the first, like, actually new definition that I want to dive in with is a dominator. So domination is a relationship between two different basic blocks. So that one block is said to dominate another block if it meets this criterion. And intuitively speaking, one block dominates another block if it is guaranteed to execute before that block. So put more formally, as the definition says, that every path from the entry of a function to a given block B includes another block A. If that's true, then A dominates B. So again, you can see how intuitively this just means that A must execute at some point in the past whenever B executes. That is, like, we know that every time we have executed B, at some point earlier, A must have executed. So that definition is fairly straightforward, both formally and informally, I think. And I want you now to try applying it to the CFG from the example function above. I have reproduced the function, the CFG here, just giving the labels of the basic blocks. I want you to take every vertex in this graph and label the set of basic blocks that dominate the given block. So next to the first block, you'll write a set of the names of all the blocks that dominate the entry block. I'm going to give you one hint here just to start things off, that this is a reflexive relation, so the entry block dominates the entry block. And in fact, that is the only block that dominates the entry block. Please pause the video now and label the rest of those blocks in this CFG. Let me show you my answers. We've already labeled the entry block. Let's label now the loop block. The ones dominating that are entry. Certainly it's true that once you execute the loop block, you must have some point in the past executed the entry block. And also that there is the reflexive aspect, so loop dominates this. We can continue on to body, and we're just sort of like building up a list of the blocks at this point. Entry, loop, and also body. Same is true of the then block. I'm not even going to write all this out, but finally it's all that same stuff, but also the then block. Things are slightly more interesting with endif, because and this is the important point, the then block does not dominate the endif block, even though it's a predecessor of the endif block. That is, it is not guaranteed that you have executed the then block before you get to the endif block, because there is a path that goes from the entry down to endif that doesn't include the then block. So the dominators of endif are entry, loop, body, and endif. And then finally, there is the exit block, the one that executes after the loop. And the important thing about the exit block, at least in this setup, because it's a for loop, is that it's possible for the loop to exit 0 times. So there is a path from the entry to the top of the loop and then immediately to the exit. So the only dominators for exit are entry, loop, and exit. That is nothing in the inside of the loop. None of that stuff dominates the exit block. Great, so I hope you have a handle on what dominators are. I'm going to show a few more definitions to you that I'll have to do with this, with giving like a little bit more context to dominance, the relationship between basic blocks. In a dominance tree, we construct it by saying that a node in the tree dominates all the blocks that are anywhere underneath. That is, all the recursive children of a given tree are all of the blocks that it dominates. So this is a succinct way to keep track of all the dominance relations in an entire function, and it is not that hard to draw. So I would like you to please pause the video now and draw the dominance tree for this function. That is, at the root, you should have a block that is not dominated by any other block. I wonder what that block might be. And then underneath that, you have all the blocks that are dominated by that block, but not by any other block in between, and so on and so on. So please pause the video now and see if you can arrange that relation into a tree and draw it on some paper. To show you my answer, it's going to be helpful to define a couple more terms. They are strict domination, immediate domination, and the domination frontier. Strict domination is just the same thing as domination, except that it's not reflexive. That is, a block does not strictly dominate itself. Immediate domination, and this is what's going to become useful when describing the tree, is that A immediately dominates B if A dominates B, and also it doesn't strictly dominate something else that strictly dominates B. So that there's the A and B, there's a sort of a domination relationship between them, but there's not a third one in between. So that's called an immediate domination. The reason I showed you the immediate domination definition is that the children of a given node in the dominance tree are the nodes that it immediately dominates. So not all the nodes that it dominates ever, those will be all the recursive children, but the immediate children are the things being immediately dominated by this. And for entry, that is just the loop basic block. Loop immediately dominates two nodes. It certainly dominates body, but it also dominates exit, and no other node goes in between. So the two children for loop in here are both body and exit. Body dominates both then and endif, neither of which dominates the other one. And those are leaves in the tree. So is exit, and this dominator tree is complete. Let me now return to these definitions a little bit farther down. The next thing that I wanted to tell you about is the domination frontier. And this one's a little bit tricky, but the domination frontier it contains nodes that are not dominated by a given node, but are just one hop away on the control flow graph. So to put it formally, the domination frontier for a given node A is those nodes that are not dominated by A, but one of their predecessors is dominated by A. If you want to think about it this way, if you have a node whose all of whose predecessors are dominated by A, then that node would also be dominated by A. But if you have one that is sort of that one of its predecessors is dominated by A in that sort of in that range of domination of a given node A, then that is then we call that the dominance frontier. So let's draw a kind of a cartoon of what this looks like. If you have a node that has like a big old tree of nodes that it dominates, that is, you can have splits and recombines in the control flow graph, you can even have loops and stuff, but the one thing that you can't have in all these nodes that are dominated by, let's call it A, is other edges coming in from the outside. As soon as you have that, that is, as soon as you have some other node coming in, two nodes that follow in the control flow graph from A, that are reachable from A, then that node is no longer dominated by A. That is, like, this is coming from somewhere else entirely. This node here is not dominated by A, but it is in the dominance frontier. So if you want to think about it this way, the nodes being dominated by A sort of form this region, and the tiny sliver of stuff just outside of that region is the domination frontier. Even more definitions. Another definition I want to tell you about is post-domination, which is the exact opposite of domination. That is, that there are, this is where domination talks about paths from the entry to a given block. Post-domination talks about paths from a block to the exit node. So what it means is one node post-dominates another node if it's impossible to reach the exit without going through that second node. So a different way of saying it is that if you know at a given block that at some point in the future it must be true that a given other block will execute, then that latter block post-dominates the first block. So there's strict post-domination, there's strict post-domination, and there's like post-domination trees and all that. It's all just sort of flipped in the opposite direction. I want you to try out this definition as well. So I have reproduced the control flow graph we've been working with. I want you to copy it down and again exercise your intuition about how dominators work, or if you like, relying on the formal definition to label the post-dominators in this tree. That is, again, for every node, list the set of blocks that are post-dominators of a given block. Go for it. Great work. I'm sure you got that exactly right, so I won't bore you with an exhaustive solution. However, here's just a few basic blocks that I called out because they're interesting. Of course, there is the exit block that its only post-dominator is the exit block. This is the analog of the same thing going on with the entry with ordinary domination. Then there's the then block, which I labeled because there's this path that goes from then through endif through the loop block and then finally to the exit. And that is the only path you possibly can follow out of this function from then. And therefore, that all the blocks along that path, then, endif, loop, and exit, form the post-domination set for that block. And then finally, I call that the entry block, where the things that post-dominated are entry itself, the loop block, and the exit block. Those are the things that are guaranteed to execute after we run the entry block. So if you want to think about it this way, those are the blocks that are guaranteed to execute in any invocation of this function ever, which must start at the entry block. Defining dominators is all well and good, but it would be really great if we had some sort of an algorithm for actually identifying dominators in a real function. This will be part of your task for this lesson, implementing the algorithm to find dominators within a control flow graph. I'm giving you the skeleton for the pseudocode, and I'm about to ask you to pause the video and fill in the pseudocode with just one extra expression to derive the algorithm for finding dominators. And then offline, your task will be to realize this in real code for Brill programs. The algorithm that I'm going to lead you to is one that, unsurprisingly, like so many other algorithms in this class, does a sort of like iterate to convergence thing. That is like loop while something is still changing. We're going to start with an empty map. So this DOM map is going to map from vertices, that is blocks, to sets of vertices. That is going to keep track of all the dominators of every block. And so when this is finally done, DOM of a given vertex in the CFG will contain a set of all the dominators of that vertex. So this is going to work by, in every iteration of this outer loop, while we're waiting for convergence, we will loop over every single vertex in the entire CFG, and we will update the domination map for that given vertex. So perhaps you can divine that like somewhere in this expression that you have to write for this, you will use the existing dominant set for some set of vertices. And you'll use that to compute a new proposal for what the dominators of this vertex are. And probably you're only going to move this set in one direction during the iteration of this loop. But then eventually, once this converges, that is like once nothing changes anymore after an entire iteration of this loop, then we should have the correct dominators for every vertex in the CFG. So this might be a little bit tricky. I don't expect you to get this on the first try, but I do want you to struggle with it for a while. So take at least a few minutes and pause the video and think of a few ways that you might come up with. It's probably going to have some unions and some intersections or whatever, some like SETI stuff for how to update the domination for every vertex in every iteration of this loop. Come up with something and argue to yourself why it might be in the right direction, and then unpause the video. Okay, here's my solution. The basic idea behind my solution is that we're going to use the current estimate of the dominators for every predecessor of this block. So the main engine that gets this work done is doing dom p for p in, and let's just call it vertex.preds. So if you think about, if this is the vertex that we're processing right now, it has a few predecessors. We have computed our current guess for the dominators for each of those predecessors. If you think about it this way, If these blocks have some dominators, like if you want to I'm just going to draw those as circles and say like, okay, all of these blocks are dominators of this predecessor. We don't know if these are shared or not, but whichever ones are shared among the dominator sets of all of these predecessors are ones that also dominate this block. That is to say, if there's any block in here that dominates this block and it also dominates this block, so it shows up in this set too, and it also dominates this block, then that means that the only possible way to get to the main block that we're thinking about here is by going through that original block first. Because it dominates this block, every path must go through here, also dominates that one, and also dominates that one. So what you have to be in order to dominate the currently active block is someone who dominates all of the predecessors of that block. So the main engine to make this work is to take the current estimates for the dominators of all of the predecessors and to take their intersection. So I'll write that as a big intersection symbol. If you think about it this way, then inside here, the type of this thing is a set of sets of vertices in the CFG, and taking the big intersection just takes the intersection of all of those sets and gives us the blocks that are in common between the dominators of all of our predecessors. To make this work, we will also need to add on the reflexive element. So we will say that vertex is also in that set. And if you union with the rest of these things, then that is a correct update rule. Just doing this, surprisingly enough, is guaranteed to converge and guaranteed to give you the correct set of dominators for every vertex in the entire CFG. I also, you will note, asked just for bonus points if you wanted to think about what the worst case asymptotic complexity of this is. You can ponder that for a moment while I slowly scroll down to the next screen where it reveals the answer. The answer is that the worst case complexity of this is n squared. That is that, like, the worst case is that we'll need to run the outer loop n times, and of course where n is the number of vertices in the CFG, and the inner loop will certainly run n times every single time. There is, however, a trick that I won't go into too much more detail here in order to make this surprisingly run in linear time. That is, in order to run the outer while loop a constant number of times. So you get a constant times n iterations of the inner for loop, and that gives you a linear number of invocations in the number of vertices in the CFG. And the way that works is just to pick the order of the vertices that you visit very carefully. In particular, if you sort your CFG in reverse post order and you do that iteration, then you get this surprising property of running in linear time. I won't go into the details about that, but if you are implementing this, then you need to run this in some order. So you might as well choose the reverse post order, which just means sort in post order and then reverse it. And if you do that, if you just process the vertices in this for loop that way, then you will get better asymptotic complexity than if you just did it in some random order. Oh yes, but I did forget to mention that this is not true for general CFGs. That is, for arbitrary CFGs, this magical reduction in complexity does not hold. It only holds for well-behaved CFGs that satisfy a property called reducibility that we will define in just a moment. That is true of most but not all programming languages, that their CFGs are reducible by default. This property is required in order to get that reverse post order trick to work. So let's move on to defining a few things leading up to this notion of reducible CFGs. The main big definition is defining what it means to be a loop. Of course, the program that we started with as the example for all of these definitions had a loop in it. And of course, that shows up as a cycle in the CFG. That is, every loop that you might write in a programming language kind of has to go around multiple times. So it really must be the case that there's a path from loop that goes back to loop. However, it will be useful to define what a loop is slightly more restrictively than just some cycle in the CFG. We will define natural loops to be something that not only is a cycle in the CFG, but only has a single entry. That is true of this loop. That is like all the stuff that is this set of vertices, because there is only one way to get into this set. There is also happens to be only one way to get out of this set, but that's not important for this example, for this definition. Natural loops have two properties. There is a cycle, and basically there's one in edge to the set. And that's all there is to it. The set needs to be strongly connected in the sense that that every node is reachable from every other node it forms a cycle, and that it also needs to have only a single entry. And this, if you want to think about it, is for a second, is true of most loops that you have ever written in every programming language ever. That is, you sort of write in some code, and then you write for or while or do or something, and then you have the code that goes inside them, and then you can think of there being an edge in the control flow graph, and there may be lots of other edges, maybe even other cycles inside the body of the loop going around. But eventually, the cycle that makes up the entire the loop gets closed at the bottom, or maybe it even comes from a continue statement, or maybe there's a break statement that gets you out of the loop. But in any case, there is no way to go from outside of the loop to jump somewhere in the middle. The only way to get into the loop is from the block that immediately preceded the for loop. And that is what's called a natural loop. If you have a cycle in the graph that doesn't have a single entry, then that does not count as a natural loop, even if you somehow created it from a looping construct in your input programming language. As an example of things that are not natural loops, this larger one, it's easier to see as not a natural loop because it doesn't form a cycle, it's not strongly connected. If we added an additional edge here, then that would fix it. This thing here is a cycle, that is like this set of 3 blocks is strongly connected, but there is an extra edge in the control flow graph from outside of that set right into the middle. So there are 2 entries to this set, so that is also not a natural loop. The way that we typically define natural loops is not just with those 2 criteria, but around another concept that is called a back edge in the control flow graph. A back edge, like the definition says, is an edge in the CFG that goes from A to B. And it must be the case that B dominates A. That is, that every way that you can get from the entry block to A must also go through B. So that vaguely looks like this. I'll draw sort of dashed lines for like the various paths that might exist in the program. Every way that you get to A from the entry block has to go through B first. There can be many different paths, but it has to look like this. So if you think about it that way, then back edges, like this solid one right here, are ones that seem to go backward from the perspective of the entry block. So one way that you can think of algorithmically finding back edges is to do some sort of a graph traversal that visits every edge, every vertex exactly once from the entry block. And if you do that and you traverse outward from the entry block, classifying every edge that you traverse from there as a forward edge, and you remove those edges from the graph and you keep on doing your traversal, then everything else that's left over, that is the ones that you didn't traverse in your sort of first outward sweep from the entry block, those ones are all back edges. That is ones that you that would go back to a vertex that you had previously visited before, so you won't traverse in something like a BFS. Those things are back edges, and they form the foundation of our typical definition of what a natural loop is. Natural loops are formed around back edges. So once you've identified a given back edge in your CFG, you can begin trying to form the vertices around that edge that define a loop that includes that edge. The way to visualize this is to think of your back edge that goes from A to B as going kind of upward on the page. B is called the header, and that is the point where you're allowed to enter into the loop. Remember that that natural loops have a single entry point. That point is called the header. Natural loops are sets of vertices L, which I'll draw as kind of this blobby set of vertices around A and B. So they have to include A and B, and has to include the minimal set of vertices around A and B, such that the following is true. You can have, if you are a member of L, this set L that defines the loop, you can have as many predecessors as you want, as long as they also exist inside L. That is, you're only allowed to have predecessors that are also inside the loop, unless, as the condition says, you, the vertex, are B. That is, you are the header. In that case, you are a special vertex that has special powers, that is allowed to have in edges from outside of the loop. But otherwise, every other vertex, including A, can only have predecessors that are inside the loop. And you can have edges that go every which way inside of here. But in the end, this is a sealed container where the only entry point is B, the header. That defines a natural loop. Finally, now that we have a solid definition of what natural loops are in CFGs, we can get back to defining that intriguing idea of a reducible control flow graph. A reducible control flow graph just says that every back edge has a natural loop. So if you think of the definition that we just looked at before, it's not necessarily the case that you can find a set of edges around every back edge such that there is only a single entry. And that wasn't true of one of those examples I showed you before. If you have back edges in your CFG that don't have natural loops around them, then your CFG is not reducible. Otherwise, it is. That is, it's well behaved, and you get that nice linear dominance finding algorithm that I showed you earlier. This is a reminder about the algorithm for finding back edges, which is just to say that you can just do a graph traversal from the entry and classifying all the edges you reach going out of the entry, like sort of recursively away from the entry. Those are forward edges, and everything else is a back edge. And then you'll be left with these back edges where this domination property holds. The surprising fact about reducible CFGs, it sounds like you just got lucky or something, but there's actually a real reason why reducible CFGs are important, which they are exactly the CFGs that you get from an imperative programming language that includes loops and ifs and conditions, and even break and continue in those loops, but no goto. That is, if you don't, goto is just like construct me this arbitrary edge in my CFG. If you don't have that and you only have the sort of nice, well-behaved post-Dijkstra language constructs to do control flow in your language, then every CFG you can possibly make with that language is reducible. So it's actually kind of a nice coincidence, I guess, that this nice way that we all believe that we should program in like goto free style way, just using the normal looping constructs of actual modern programming languages, yields well-behaved CFGs in the way that we saw before. I would like you now to think for a little while about, to solidify your understanding of what a reducible CFG is by drawing some irreducible CFGs. So in a moment, please pause the video and draw at least one control flow graph that is just a directed graph that is irreducible. That is, it has a back edge that you can't form a natural loop around. Give it a shot. There are, of course, infinite possibilities for irreducible CFGs, but I'll show you a really small one. All you need are 3 vertices. You can think of this one as the entry block. If this block goes to both of these blocks, and these transfer control to each other, then we have an irreducible CFG. If you think about it this way, then if you try to identify the back edges in this graph, if you take our algorithm to run like a BFS or whatever to traverse the forward edges and you're left with back edges, then you actually have some ambiguity. And it might be the case that this is a back edge, or it might be the case that this is a back edge. But in any case, if you try to form a natural loop against either of those candidates of back edges, then it has to definitely include these 2 edges. But then also you are stuck with having 2 entries into this thing that might be a natural loop. And of course, natural loops have to have a unique entry point, so this doesn't fit, and this is an irreducible CFG. So that has been a lot of definitions. I want to show you something you can do armed with this information about CFGs to actually optimize programs. In particular, I want to show you a optimization called loop invariant code motion. Loop invariant code motion does exactly what it sounds like it should do, which is to take code from inside of loops and move it to outside of loops. So instead of being executed n times, it gets executed only once for the entire loop. So this is a little schematic of a program that has some loop invariant code. So if A and B are like assigned outside of the loop, and you don't reassign A and B, and you just multiply A times B inside the loop, that's wasteful. It would be much better if we could hoist A and B outside of the loop, because it's loop invariant. It doesn't vary with every iteration of the loop. So let's just compute it once and reuse it multiple times. Loop invariant code motion will use natural loops, of course. It will look inside of natural loops, and it will try to move code outside of them. So one more definition here, there's something called a pre-header associated with natural loops. natural loops aren't guaranteed to have a single preheader. That is, if you follow our definition, it's possible to have like, there's your entry block, and you got a big old loop going on here. That's the natural loop. It's possible to have lots of blocks that jump into that unique header block. However, it's often convenient when doing loop optimizations to make the preheader block unique. And that's actually not that hard. All you need to do is to take all of those edges that previously went into the header of your loop and reassociate them with an empty basic block that all it does is jump to the header block. Now we have a unique preheader block that is guaranteed to be the thing that executes right before you start doing the loop. And if you do that, then we have a destination for moving loop invariant code. That is, if we were to find like A times B somewhere in this loop, and we were to classify it as loop invariant code, then we could remove it from there and move that code to this place, to a place where it can be safely computed ahead of time and then reused multiple times inside the loop. So let's look at how to do loop invariant code motion. Here I have rewritten the code just slightly into a little bit more of a Brill-like form, where computations are kind of atomic and happen at individual instructions. So there must be an instruction somewhere that looks like the product, that is the A times B that we wish we could move. Our job in loop invariant code motion is just to identify those instructions that are loop invariant, and then in a second phase, move those loop invariant instructions to the preheader. Assume that we had already invented a unique preheader for the loop, and we just need to move that instruction. And so if we use the R value inside the loop, then that will be assigned once and for all in the preheader outside of the loop. So just to recap, we have taken this somewhat undefined problem and made it slightly more concrete by taking it to the Brill domain, and now we only have to worry about instructions, moving individual instructions. I want you to think about this for a little while. I want you to think about how to accomplish those two steps. This is a very open-ended set of questions, but I want you to think about how first you classify instructions as being loop invariant. What are all the properties that make an instruction a candidate for being movable outside of the loop? Think about ways you could break the program if you're not careful, so that you can be absolutely sure that when you classify an instruction as loop invariant, it is safe to move. And then second, I want you to think about how to actually do that. That is, when it is appropriate to take an instruction that is loop invariant, and when is it possible to move that to the preheader of the loop. Moving it will just consist of like deleting it from its context and appending it to the bottom of the preheader. So break the problem into these two steps: classifying instructions as loop invariant and classifying loop invariant instructions as safe to move. Try to ponder through this for a while. Again, this is so open-ended that there's not like a particularly right or wrong. I guess there are wrong answers, but there's no single right answer to this question. So try to think of the criteria as you would write it and think of it in a sort of algorithmic way that you could possibly actually implement, and then unpause the video. I wrote my answer in the form of pseudocode, maybe unsurprisingly. I wrote the pseudocode that does this whole iterate to convergence thing. And its job is to mark every single instruction in the loop as loop invariant or not loop invariant. So the way this is going to work is iterate to convergence while processing and over process every instruction in the loop. And slowly we're going to mark more and more instructions as loop invariant until we can find no more, and then we'll be done. We'll have added these markers everywhere that we can. And the criteria for marking a new instruction as loop invariant are actually fairly straightforward. However, they do rely on one trick, which is that you should have already computed reaching definitions. Reaching definitions, recall, was one of our data flow analyses. If you have that, then you have the information that you need in order to decide whether definitions come from outside of the loop. This definition is able to make comes from more precise. That is, we mark instructions as loop invariant depending on all of their arguments. That is, if all of the arguments were originally defined, if their reaching definitions, all of the reaching definitions for a given variable are outside of the loop. Remember, we had this computation A times B, where A and B both sort of came from outside of the loop. Those would show up as all the reaching definitions of A and B being outside of the loop. If that's the case, and you do something like multiplication that's like a pure operation on those two things, then you have a loop invariant computation, because every possible definition for A and B was itself outside of the loop. Or the arguments to your instruction can be themselves already marked as loop invariant. So for example, if I were to put this A times B in a variable, and then I were to do like y equals x times b, for example, then in the second iteration of this outer loop, I will have classified the first instruction as being loop invariant, and then I can use that to classify the second instruction as loop invariant. So you think about it this way, it's just sort of treating those loop invariants markers as being the same as having the definitions outside of the loop. So if you've already decided that something is loop invariant, then you can conclude that that argument is safe to use in a loop invariant instruction. So this is my algorithm for identifying instructions that meet the conditions of being loop invariant. However, the reason I asked you to split this off from deciding whether it's safe to move that instruction to the preheader is that there's a few more nuances that don't just have to do with this simple property of having computations whose answer only depends on variables from outside of the loop that don't come from, that don't change from iteration to iteration. So I have these criteria here for when it's okay to take a loop invariant instruction and to move it to the preheader. So the first one is that the definition must dominate all of its uses. So this is to say that there must be no use of that variable that might come from somewhere else. If you think about it this way, then a natural loop looks schematically something like this. If you find a loop invariant assignment to, for example, x here, and there is, however, a use of x on the right-hand side here, then that's a danger, because while this computation is loop invariant, it's not safe to move, because if you move it, you will be changing the definition of x for this use of x. So we have this criterion that every definition that every loop invariant definition must dominate all of the uses. That is, it's not possible, it is not just that this x sometimes comes from this assignment x, but every single time those reads of x must come from this definition. Then it's okay to move it to the preheader. It is also a good idea to say that there are no other definitions of the same variable. This is just dealing with naming conflicts. It's not that interesting. This last one, however, is a little bit of a bugaboo. It says that the loop invariant definition that you want to move must dominate all loop exits. Remember that it's possible to like get out of a loop at many different points. You don't need to have like a single exit point, like you have to have a single entry point. And your assignment needs to dominate all of the exits. And the reason for this is that way you can be guaranteed that that computation would have run anyway. That is, it's not possible for some path through the loop to skip that assignment. And therefore, by moving that assignment to the preheader, you are computing and overwriting a variable that that you wouldn't have overwritten in some executions of the loop. In particular, this becomes a little bit tricky, even for the example we just saw, which is that very often when we write like for loops and stuff, we have a loop that looks like this. That is, here is the natural loop we are concerned with. Here is the preheader that gets into it, and there is a path from the header that goes outside of the loop. And this means that nothing inside of the loop except for the header actually dominates all of the exits. And the reason for this, I mean, it's very important that it is possible for loops to execute only 0 times. Most loops that we write, at least most loops that I write, have the possibility to execute 0 times, and that's actually nice. Of course, there are constructs in lots of programming languages like do, while, for example, that are guaranteed to execute once, and these do not have this problem because there's an exit that is dominated by everything that's inside the loop, unless you use break, of course. But for normal for loops, this actually seems fairly limiting. We can't move instructions from for loops that aren't loop invariant instructions that are not in the header, which of course is like probably most of our actual computations are going to be outside of the header. So how do we deal with this? It is actually possible to relax this last bugaboo of a criterion if you obey a few other things. That is, if you are sure that the destination variable is dead after the loop, that is, like by assigning to that variable spuriously, even when you didn't need it, even when the loop executes 0 times, you're guaranteed not to be clobbering a variable that somebody else wants. And there's one more thing, is you need to be really, really sure that you can't cause problems by doing needless computation. It is probably fine to multiply stuff, for example, but it is almost certainly not fine to divide stuff, because if you end up doing a computation that you might not have done otherwise in normal execution, unoptimized execution of the program, and that instruction might throw an exception, like with a divide by 0, then you can introduce exceptions where the programmer thought, quite reasonably, that no exceptions were possible. And that is just the way for any optimization you might do that can be classified as speculative. An optimization is speculative if it does extra work, if it is possible to do extra work just on just guessing that work will be useful in the future. If it's possible to do wasted work that will never be used and doing your optimization, then that's a speculative optimization. And they can often be really good ideas because you're optimizing for the common case and then and increasing the cost in the much less common case that your loop executes 0 times. However, you need to be really sure when you do this kind of speculative optimization, that you don't introduce extra exceptions. So doing stuff like divides, you need to do very, very carefully. That's loop invariant code motion. It's our first actual honest-to-goodness global optimization on functions. In the next video, we're going to see how to convert programs into SSA form, which enables all kinds of other optimizations that can act on entire CFGs.